Well, it's 11:10. I'll go ahead and get started. I have too many slides as usual. Okay, so my name is Chris Drake, as you mentioned. We're here to talk about a library I wrote called PyEDA, which is a Python library that implements several data structures and algorithms for electronic design automation. And I'll explain what that means as we go through the presentation. It's a very, very broad topic, and I'm actually going to be a little bit more specific than that. So about PyEDA, it's really, it's a nights and weekends kind of project. I'll explain the motivation in a minute. The source code is on GitHub, and the documentation is on Read the Docs. You can pip install it if you have a C compiler. But if you're using Windows, actually I would prefer you to go to Christoph Galke's page if you're familiar with it. He's got some excellent Windows binary distributions of scientific software. It's really excellent. The guy's a superhero. So like I said, it's a hobby project of mine. Though in the last several months, I've been getting a lot of emails from people. Most of them students. People asking me to maybe help with their homework a little bit, but also a few people like at Vanderbilt University and University of Saarland who've been just sort of using it for offhand things. And I even got an email from somebody who was, if I can remember this correctly, she was using it to study sort of how global warming impacts bird migration patterns or something like that. So it seemed like it was time to go out and sort of explain some of it to people. And so here I am. And they say you should never start off a presentation with an apology, so I won't. But it also is not to be confused with a few other very similarly named things. And I've had it on my to-do list for way too long to sort of rebrand it with a different name. So when it gets to version 1.0, maybe I'll think about that. Okay, so there's too many features to really talk about them one by one. Like I said, I actually have some demo stuff, and if we get through all the information in my presentation, I'll show you some interesting stuff in some notebooks that I literally just uploaded to GitHub like 5 minutes ago. I want to start with a little bit of motivation about why. Why am I working on this? He mentioned that I work at Google, but I'm not really here representing them. This is just something that I do on my own. And so after that, I really want to talk about more specifically Boolean functions, because you may know what a Boolean function is, but you may not have considered all of the engineering trade-offs associated with actually having to implement Boolean functions on a large scale and actually deal with them, in chip design. So yeah, that's the basic outline. We'll try and breeze through this. It's really broad. We're going to go through a lot of these slides really fast, and so if you want to go into any of this info in more depth, I recommend going to the documentation. So this is a typical chip design flow, and the movie Minions is coming out, or came out already. And I actually used to work for Intel for quite some time. And if you're your average minion who is being asked to do a chip design, you'll start off with what's called hardware description language, and you'll go through a verification process. That HDL, typically written in Verilog, will be synthesized, and it goes through some sophisticated what are called place and route algorithms to really place all those logic gates onto the floor plan for the chip. And it'll come out the other end in a GDS2 format, which you'll then send to the factory for manufacturing, and you get your chip back. Well, what's missing from this picture? And by the way, don't email me that I left out Specman. There are other languages involved in chip design, but what's missing here is Python. So if you're like me and you're a minion and you develop sort of a profound sense of sadness, if you can look at him, he's kind of sad, then you come up with a three-phase plan to change the world. And so the three-phase plan is literally just, Python, C, and EDA something, and then question mark, profit, right? So that's kind of where we are. And but I think that you might be interested in it, especially the stuff on satisfiability. I should also mention that there's a lot of methodology evolution going on there. There's a couple really exciting Python projects, PyMTL from some guys at Cornell, MyHDL, which is a really great Python logic simulator. Also compiles to Verilog, and some other stuff, high-level synthesis, BlueSpec, and a Scala library called Chisel, which is really exciting from guys at Berkeley. So let's talk about Boolean functions. This is really sort of the gist of it. If you've never really done much work with Boolean functions, they're like regular functions, except the inputs are restricted to 0 and 1, right? We're talking about digital logic here, okay? And so what's really interesting to me, and what I learned a lot about during this process, was that there's a lot of different ways to represent Boolean functions when you actually try to work with them mechanically in a computer program. So you've got tabular formats like truth tables and implicant tables. You've got a whole family of what are called decision diagrams. And unfortunately, I don't really have a lot of time to talk about them. If I have time at the end, I'll show you some examples. And also, the typical ones, like the ones that would be implemented by SciPy, for example, are graph-based data structures like logic expressions, which I'll talk about today, and inverter graphs. And a new one, which actually came out, or didn't come out, but which I learned about at DAC this year, is Design Automation Conference this year, is the majority inverter graph, which I also want to talk about. So PyEDA implements some small set of these. This is obviously a work in progress, but so these are sort of the major families. And like I said, I'm mostly going to talk about logic expressions. They're really kind of the workhorse. And implicant tables don't really have a user interface. They're related to logic minimization. So I'll talk about some of these in detail in this presentation. So let's start with logic expressions and also satisfiability, because this is a really important algorithm that you guys should know about. So a logic expression looks like this. This is how you would construct one. You can, PyEDA overloads Python's logical operators. So you create some variables. See here A, B, C, and D. You use the logic operators to construct these expressions hierarchically, and so this is what you get. So this is a graph, a directed acyclic graph. At the leaves are the what are called atoms. In this case, A and negative B, et cetera, are literals. And at the branches are operators. And also, if you're sort of too lazy to do, to use the logical operators programmatically, you can actually just parse an expression as a string. I've implemented a top-down recursive descent parser to parse Boolean expressions for you, so you can do that the same way. So there's a litany of features. I won't have time to talk about every single one, but probably the main takeaways here are that the logic expressions themselves are actually implemented in C ever since the 0.27 release, and I'm currently on 0.28. The really killer app here is that I have a very nice integration with the picosat sat solver. I'll talk about sat in a minute. It implements other things, negation normal forms, complete sums, a lot of operators you may not see in other libraries. Talk about satisfiability. So this is a really fundamental question. Given a Boolean function, can we assign its input variable some value so the output is equal to 1? And it sounds like kind of a mundane question, but it's actually one of the most important questions in computer science. And PyEDA implements satisfiability. Either you get one satisfying assignment with satisfy one method, or all satisfying assignments with the satisfy all iterator method. And it has a lot of applications for digital design. But rather than go through these one by one, I thought I would mention, it was kind of timely, Donald Knuth recently released The Art of Computer Programming Fascicle 6a. It's an entire chapter dedicated to satisfiability, and it's really fast. I didn't get a chance to read it yet. It's like 100 pages long, but there's a lot of really useful algorithms for optimization problems and so on. Digital tomography. I don't even know what that is, but if you need to do graph coloring or something, you should probably be familiar with SAT. And so I want to explain to you a few interesting things about SAT. So first of all, modern SAT solvers require what's called a conjunctive normal form expression. And so that's a two-level expression of and over or. And there's a problem that you may run into if you're constructing arbitrary logic expressions, because like in the picture I drew earlier, you can construct an arbitrarily deep logic expression. And as you compress the logic expression down to two levels, you actually get this kind of exponential blow up. And you can see here, I've got a couple terms, two and terms. When you distribute that or over that and operator, it becomes 4 because you take this the cross product of those terms. And so there's a solution to this, and it's called the Tseitin Transformation, to take some arbitrarily deep Boolean expression and convert it to a conjunctive normal form expression. And again, this is kind of a deep topic, which could be, I guess you could devote an entire lecture to this, but the basic gist of it is that you take your tree, and for every single gate in your tree, you assign that gate to be equivalent to some variable. And then you create a list of constraints that says this node is equivalent to the same operator with all of its inputs substituted for its subgraph variables. And like I said, I know that's a lot to sort of take in, but the basic the basic takeaway is that in polynomial time, you can take an arbitrary depth expression and you can convert it into a conjunctive normal form because that transformation, that last level transformation, when you take that list of constraints, you say this constraint and that constraint, to convert that into individual CNFs is actually very, very easy. And so then you can solve it using picostat. And so this is actually kind of a killer app that you guys should know about if you're dealing with these arbitrary expressions. And not implemented by too many libraries out there. I think I saw one implementation in a library called Yosis. So anyway, I mentioned binary decision, so moving on, excuse me, but I mentioned binary decision diagrams earlier, but they're really, really fascinating data structure, and I really don't have time to talk about everything about them. And also, the version that's implemented in PyEDA is actually implemented in pure Python, and the Python interpreter imposes kind of a large overhead over the implementation. And so if you really want to use it for industrial strength stuff, it's probably not what you want, but for education, it's really useful. What's interesting about BDDs is that they're a canonical expression form. So no matter how you construct it, unlike logic expressions where you can kind of construct them in arbitrary ways, and it's hard to tell whether those expressions are equivalent, with BDDs you can construct it in any way you want, and you'll always construct the same BDD. So let's get to truth tables and minimization. Since I got the yellow card, if I have a minute, I'll get to the example. So if you've taken a basic digital logic class, you've implemented truth tables. This is how you'd implement them in PyEDA. This is F1 here is an OR function, and F2 is an AND function. And also you may, if you take your undergraduate or sophomore digital logic class, you may have played around with something called Karnaugh Maps, right? And so a Karnaugh map is a way that you can take a function cover and implement a disjunctive normal form from it. So, like I said, who here has done Karnaugh Maps? Okay, so I see a few hands. So you're probably getting some great memories from your sophomore year of college now. I'm bringing it all back to you. And so you can construct some DNF expressions like this. Well, there's a problem with this method. And the problem is, well, how do you deal with more than 4 input variables? It turns out it's really, really hard. I mean, you can do it, but you'd need a really large set of graph paper. There's something called to implement logic minimization. I took the Berkeley C Espresso logic minimization code. So Espresso is an algorithm that heuristically minimizes an arbitrary disjunctive normal form expression. And it'll try to find the least cost implementation of that. When I mean cost, what I'm talking about is the cost in an actual implementation in a circuit. And so if you really need, first of all, this is another really hard optimization problem. And if you give it an arbitrarily large expression, it'll probably work really hard on it. But in practice, Espresso does a pretty good job. So if you need that functionality, you can also minimize those functions together. So briefly, I'll cover function arrays too. Sometimes one function is not enough. You need an actual array of functions. And you can use PyEDA's factory function to create NumPy-style slicing function arrays. So you can see here the EXPR vars. That's creating a 4x4x4 array of expression variables. And you can slice them just like you can in NumPy. And you can also use sort of vector-wise operators. And so you can see, I know there's a lot of information on the screen, but that star is is a repetition. It's treated like a Python list. When you multiply a list, it repeats the list. And you can also do a vector XOR of two arrays of functions together. And also, if you want to use, it has an F-array constructor, so you can arbitrarily create sort of shaped arrays of functions if you want. And what's really nice about this, what I find is nice about this, is that you're sort of approaching a nice domain-specific language for being able to deal with arbitrary Boolean algebra involving vectors of Boolean variables and functions. And so you can see here, the example I've got here is a function from the AES algorithm, which does an X-time operator. And you can see there's like a plus operator, an AND operator, a star operator. I mean, all these things are basically overloaded using Python's overloading capabilities. And you can actually approach something that looks like a DSL. So, demo. I haven't received the red card yet, and when I do, I'll probably just stop. But the demo I have is I want to show you a couple functions. So here is an implementation of, I mentioned before, and I moved over it so fast it's worth sort of mentioning. Logic expressions they're not a canonical form. So you can construct logic expressions in many different ways, and they may or may not be equivalent. So here's this is the bit number 2 of a ripple carry adder. This is the one I'm looking at right now, the sum bit of a ripple carry adder. And here's bit number 2 of what's called a Kogi-Stone adder. And they are the same function, but they look very different. So if you're kind of an observer and this function starts to get really, really big, it's really hard for you to tell, whether they're equivalent. And that question of whether they're equivalent is actually very important because, as it turns out, you can formally prove the equivalence of functions, and it's a very important application in digital design and verification especially. And so the way you do this is you take those two functions and you take their XOR. And if you guys remember what the definition of an XOR operator is, if the inputs are different, then it outputs a 1. But if they're the same, it outputs a 0. And so you can see, I'm going to do this experiment for sum bit number 9. So you can see if the sum bit number 9 is some deep expression, if the XOR of those two functions is not satisfiable, then the functions f and g are equivalent. And so we're going to use all of our newfound satisfiability knowledge. So first we're going to take f as the XOR of the two functions, and I'm going to wait about, I think, 5 seconds to get to see whether it's satisfiable. And it says here it took about 1.68. Well, that's using a very naive backtracking algorithm. It's basically just kind of walking through all the possible inputs recursively. But if I do the Tseitin transformation on that, and then I do the same SAT calculation, you can see it's only 106 milliseconds. So you see, this is a very powerful method if you really need to do these complicated formal equivalence checks. And unfortunately, I'm out of time, and so now I'll answer your questions.
Any questions?
Yes.
Do you have a recommendation for the resource like this stuff? I remember I really enjoyed my class, but
Oh, that's a really great question, and I have a great answer for it. There's a course. Oh, sorry. The question is there a good resource to sort of learn about it and think about it, and the area of digital logic and this kind of stuff? Maybe EDA in general. There's a great class in Coursera. The class is called VLSI CAD. It's offered by the University of Illinois. And I think that the stuff that I've talked about today is basically like the first 2 or 3 weeks of that class. So yeah, I would definitely recommend that. As a matter of fact, I've actually been on the forums of that class, and a few of the students have used it periodically for some of these things. So yeah, it's a great resource for that. Any other questions?
So thank you again, and enjoyable talk.
All right. Thank you.